So we talked about induction in the previous class. And as I mentioned, so it is, I mean, we are just giving some examples, but these are, I mean, I think these are the examples that also talks more about it. So this is one interesting thing about this book is that it tries to actually talks more about try to talk more about induction to design algorithms. And this is like somehow induction and algorithm design is very related in this book, which is, I think, actually, I like it. And in some sense, I mentioned also, I mean, about the general rules of induction. So I mentioned that you want to have it, like, for example, you make a start with the case of 0. So this is very important. This also, you will see it in all these lead code problems, or I don't know, hacker rank and other ones, or geek for geeks. There is always a parameter n. Sometimes there might be another parameter m as well, but these are the main parameters. And after that, you need to read the input based on n and m, essentially. So if there are both n and m, generally I will call n plus m. You can just consider n plus m, and this is the one that I will call it n. So what is n whenever I'm talking about means if there are several parameters, just sum it up, that would be n. That would be larger than any parameter. So that is the unique parameter that I'm talking about. So you want to prove something in terms of n, the main parameter. This n can be 0, n can be 1, n can be 2, and it can be, I mean, anything. So the main important thing is that you want to make sure that when you do this reasoning, you can reach any integer n. And we discussed before that actually sometime, I mean, this is a regular induction. This would be like a strong induction that you will use all previous guys to prove these guys. For n equal to like 3, you are not using just 2, but 0, 1, and 2 case. This is called a strong induction. Or there are, I mean, something it is called, I mean, more general inductions. That is like something like this. Like first, you will prove for the power of 2 to the I for, like, I don't know, for maybe 2 to the 0. So this is n equal to 1. Then you are doing it for 2, which is 2 to the power of 1. Then maybe you will do it for 4, which is 2 to the 2. And maybe then you are doing it, I don't know, for these are, you are doing it essentially for power of 2 to the n. So that actually you are doing induction on the powers. Once you had that one, so you will reach from here to here, from here to here, from to here to here, or something like this. But then you may need to come back and you will prove it in the next, another induction. You will prove everything in between also is correct. That's the type of induction that you will see it in this book. And the general idea for induction is that there is a path from 1 to any particular number. And if there is a path, means that this is essentially correct. So sometimes you can see the whole induction as some kind of algorithm. That good. Let's just give you some examples of this, I think, induction to check. Is it clear so far? Any question? If there's a question, please unmute and ask questions. Great. So, okay. So I assume there is no other question, but please, I mean, unmute and ask question whenever there is questions. That would be great. So this is one example, I mean, that we want to do that. This is the first example. We want to say that for all natural numbers x and n, x n minus 1 is divisible by x minus 1. Good. So let me just change the things. Good. So of course, for the case of for the case of n equal to 1, we are considering which would be x minus 1 should be divisible by x minus 1. So that's trivial. Now, you want to say that, assume that it is correct for n minus 1. Generally, I mean, when we talk about it, you can go from n to n plus 1, but maybe easier to go from everything less than n to n. Now, let's go essentially say it is correct for n minus 1, then I want to get it for n. So how can I write this one? This is the formula essentially that I'm writing it. So I will just write xn minus 1. You can just, this is a simple example. You can just factor x there. You can write it like this, plus x minus 1. So now, where do we use? So this is xn minus 1, xn. So this is we are doing for n. We turn it to n minus 1. Now you can see, for example, this is trivially x minus 1 is divisible by x minus 1. And xn minus 1 minus 1, this is divisible by induction hypothesis. So induction hypothesis says that x minus 1, this is divisible. This is the induction hypothesis. Xn, x to the n minus 1 is divisible by x minus 1. And then we will prove this statement for xn minus 1. Clear? So this is another one that actually we are using it a lot in this course, the formula. We want to say that the sum of the n first natural numbers is n times n plus 1 over 2. Okay, so I mean, for n equal to 1, this is the basis of induction. So we need to say for basis. And let me just okay, so this is the basis of induction that for n equal to 1, it is the sum of them would be n equal to 1. You will put it is equal to 2. Now, assume it is correct for the first n natural numbers. Now, I mean, here we are doing it n plus 1 versus n. I mean, to just have some thing. But generally, you can go from n minus 1 to n. That would be easy. But this is just example that we are doing. So what is the Sn plus 1? This is the sum of the first n numbers plus the number n plus 1. So here, I mean, by induction hypothesis, we know that the first n numbers, the sum would be n this one plus this one. So you just sum it up, and then it would be n plus 1 plus n plus 2 times n plus 2 over 2, which is exactly the one that we want to prove. So essentially, we will do that. One important thing that's actually is important when you write papers and maybe for assignments. One other also thing that would be used for assignments. This is not a requirement, but if you can do it, it might be good if you do it by LaTeX. Good. So, for example, I mean, you can use Visual Studio Code or Overleaf, and it would be good. I mean, maybe for some, if you, I mean, you are busy some week, you don't need to do that. But if you have more time, I think it would be good to do that. That actually improves your LaTeX skill that you also need it for the projects as well. By the way, how many people have used LaTeX before? I will say more, they are professional in LaTeX. Okay, so that's good. So I think for the people who have not used it, I think that might be good. So this is, again, this is some of the things that I'm talking about it because this is the honor class. I want to keep the standard hard, I mean, high, and this is the one that we are also doing it for graduate courses. So for some of these things, for example, like for this class that we have it. I would like that. I mean, you are doing more LaTeX, and again, I mean, just you can use Overleaf or VS Code. Both of them would be good. For some of the assignments, at least try to do that. It's not a requirement, but it is strongly suggested because then you become familiar with LaTeX, and LaTeX is the language that wherever you want to write it. Okay, I have written in companies Word as well, but generally, if you want to, in these companies also, if you want to publish papers, you need to do it LaTeX. Like I'm, for example, editorial. Like I'm editor-in-chief of Algorithmica. This is the oldest existing journal on algorithms. And generally, whenever there are papers that are submitted in Word, it seems that they are not high-quality papers. So you may send such a bad impression to the people that the quality of the paper is not good if you are doing by Word. Try to do this write in LaTeX for the assignments. And I mean, for the final project as well. For final project, you need to use LaTeX. That's the requirement. But I don't want to use Word for that. But for assignments, also please do. One other thing that I wanted to mention about the writing. So this is actually important way of writing. When you write it, the formal proofs, you need to write it essentially in English, but sometimes you have the formula. This is actually, there are two ways you can do it. Maybe you can put something like, if you want to write it in text, maybe you can put some number 1 here or something like this on top of these equations. And then after this proof, you will say that, note that the equation 1 is correct because of induction hypothesis. So this one, you can say 1, and then you will write it down after this statement that it is by induction hypothesis. Sometimes the people are writing it also in a few lines. And then, for example, it might be like this. So they will say S of n plus 1 is equal to S of n plus n plus 1. And then in the next line, say that it is equal to n plus 1 over 2. And then here say that plus n plus 1. And then here they will say that by induction hypothesis. So there at the end of the line, you are writing this. So for example, again, you will just say it is equal to n plus 1 times n plus 2 over 2. And then here you will say by some by some simple algebra. Good. So what is the idea? The idea that any equation, or essentially any equations or any inequality that you will write it, either you need to put some number 1 and then describe that 1 comes because of induction hypothesis, or you can write it in multiple lines, and for each line you will say the reason. That's very important to have a very nice written papers. That's the one that I think it would be good to have it, that you can mention by the end of the line that why we have this equation or inequality, etc. This is a very written paper, and you should always do that. Great. Any questions so far from the way of writing, etc.? That's very important, actually, that you should write it in a professional way in your assignment, in your exam, in your project. Any question? Please unmute and answer if you have any question.
What is the induction hypothesis in this question?
Which one?
This example two.
Yeah, so this is induction hypothesis. Thanks actually for the question, because that might be question. So induction hypothesis would be exactly this. Sn is equal to this number. So induction hypothesis would be Sn equal to n times n plus 1 over 2. That's the induction hypothesis. Clear?
Yeah, okay.
So we are assuming that it is correct for n. So generally, induction hypothesis is just a statement for previous values. So in this case, we want to prove it for n plus 1. So induction hypothesis would be that for n. It can be actually, you can say for all values 1 to n. That is fine as well. But maybe in this case, you don't need, for example, from n plus 1, you only go to n. You don't need n minus 1, etc. Clear?
Yeah, clear.
Any other questions? Great. So let me clear all drawing. Good. Let's go to the next problem. Okay. So what is this one? So it says that if n is a natural number, so natural number means essentially number from like a whole number, say. And generally natural number means greater than or equal to 0. And if we have this assumption, 1x plus greater than 1 plus x is greater than 0, then 1 plus x to the n is greater than 1 plus nx. That actually is an equation that I think is a very important equation. The people will use it a lot. If you want to prove anything, to approximate anything, that's actually a very good approximation. Good. You want to say that for all natural numbers n, means essentially n is a whole number and n is greater than 0. 1 plus then 1 plus x to the n is greater than 1 plus n times x. Good. Now, again, first you need to, this is for the basis of induction. For n equal to 1, essentially both things would be equal to 1 plus x, so we have the equality. Now, again, now what is the induction hypothesis? I will write it here. So induction hypothesis is that induction hypothesis essentially is this one, that for n, the statement of the theorem that we want to prove is correct. Now we are proving it here for n plus 1. So again, I mentioned that you can go from less than n to n, or from n you can go to n plus 1. Yes. So let's do it now for n plus 1. So what do we do for n plus 1? So for n plus 1, we are just writing trivially here. So here, for example, I mean, you don't need to see anything. That is maybe simple. Now here, this is the one that you should put 1. And why is it correct? The reason is by induction. So what can we say that? We can say that, okay, we have written this one is like this. Then we can write this guy. So 1 plus x is like we write it 1 plus x. And then here, instead of 1 plus x to the n, we are writing 1 plus nx. That's the thing that we are writing. Good. Here we are using two things. You see, this you can write it down. Note that you will write it down. Note that the inequality 1 comes from two things. First is that by induction hypothesis, because we knew that this part is greater than this part. That's by induction hypothesis. The other thing is that we know that 1 plus x is greater than 0. This is the assumption. So, and then, so it comes 1 by induction hypothesis. And the second one is the assumption that we had 1 plus x is greater than 0. This is the same assumption that we had in the statement of theorem. So please unmute and answer. Why do we need this second condition that 1 plus x is greater than or equal to 0?
Because if it's less than 0, then the inequality would flip.
Exactly. So we really need this one. I mean, we can only say essentially something, we can replace this one with something smaller and it still is correct if the other term is positive. If the other term is negative, if we do it this one, actually, as you mentioned, the equation actually flips. So then we have this one, we obtained, but these are exactly the one that in a nice writing should be mentioned. So you can say that one, I mean, again, you can do it two styles. One, each of them, I have written it here in one line. You can write it in one line, but you can put this number 1 on top of this equation, these equations. Maybe just format it is clear. So you can just put, this is 1 that we are putting on this equation. You can put 1 and then explain 1. Why do we have 1? Why? Because of this part, essentially. Or you can write it in multiple lines, and at each line, at the end of the line, you will say that's why. So you can break the line here, and break the line after here, and then explain why we have these properties. Great. That's the beauty of, I think one of the beauty of Zoom that I love it is this clear things that you will put it. But otherwise, if I wanted to even write it in pen, nicely, I couldn't just nicely delete those guys and everything back to the normal. But here by a click that happens. Anyhow, so we have that things. Good. So now what do we have? We have this one. Now we want to say, why do we have equality? So we talk about this one. Now we have equality. But here, this is the one that is said by simple algebra, essentially, or simple math. You will I just multiply these guys, it becomes this one. Then again here, this is the equation 2 that I will call it. Now we have this one, then we are done. Why? Because this is the thing that we are using again. So we can say that this is greater than this one if this is positive, because then we are just removing something. If we remove something from here, it just goes down. Why this is positive? Because we have n, which is positive, which is natural number, and x to the 2, which is also positive. So this is the whole thing is positive. And again, you can explain that 2 happens because nx to the 2 is positive here. So nx to the 2 is positive. Great. And then we just get the results that we want. So this is the statement that we wanted to get it for n plus 1. If you put it n plus 1 would be this, I mean, the statement would be this plus this greater than this n plus 1 times x. Exactly the statement that we have proved. Any questions? Great. Let's go for the next. These are the more deeper problem that to talk about it. So what is the problem? You are given a set of lines in the plane. So you are given a set of lines in the plane. And we say that this is a general term that you will hear. We say that we are in a general position if no 2 lines are parallel and no 3 lines intersect at a common point. So this is a set of lines that are given to us. Say these are, say, infinite lines, essentially. Go to infinite. And we say that they are in a general position if there is no parallel one, no something like this, and no 3 lines that are going at the same point. So this is also not. And then we call it they are in a general position. This is a statement. The number of regions in the plane formed by n lines in the general position is n times n plus 1 over 2 plus 1. Good. So, for example, let's see that if the number of lines is 0, how many regions we have? Please unmute and answer.
Just one region.
We have one region. If we have one line, what is the thing that we have it?
2 regions.
How many? 2 regions. And again, these are some infinity lines. You can, I mean, you don't need to actually have the infinity. You can actually consider also a large thing so that it is some line like this. So this is the whole thing is a page. So this is say the boundary. So if you have one line, then you have 2. Now, what about if we have 2 lines? How many regions do we have?
4 regions.
4 regions. Good. So it seems that it is correct. So if you put the formula for n equal to 1, for example, it would be 1 times 2 over 2 will be cancelled. So it will be 1 plus 1 would be 2. And you can check it essentially for n equal to 3 is correct. And so you want to prove this one. So let's do this one. So we want to prove this one, these n lines. If they are forming in a general position, the number of regions is this one. Good. So this is the way actually when the larger proofs are coming. So you might see, I mean, read some proofs, and the proof seems, I mean, a complicated proof. The question is, how do the people obtain the results? Generally, the idea is that you need to, this is like, say, this is a type of thing that you need to break the problem into a smaller part and then conquer each of them essentially. So this is like somehow this is called divide and conquer, or I will say break and conquer. So to prove this maybe is hard. So let's have some smaller things. Generally, I will call this one as a theorem. To prove a theorem, we may need to have some lemmas. So these lemmas are the one that the people will, like, for example, you can do it also in your project. You may want to have something, some bigger theorem, but to prove that, you may need to have some simple lemmas that you can, like simpler lemmas. There was actually a paper I was reading it. It is in the math paper. So there was a theorem. It is called. This is the graph minor. So it is called graph minor theorem. So the proof of this theorem, this is one of the hardest things. The proof of this theorem is something I will say more than 500, 600 pages. And this has been published maybe in, I will say, I think, I don't know the latest one, say like 25 papers actually. There was one paper that it is mentioned that, this is, it was 40 pages. All pages. So one of this, this is like the one of these journal papers. This is the abstract. This is the lemma. The proof is like 40 pages. It said, "Is this paper we are proving a lemma that will be used in the future papers to prove this graph minor theorem?" This is by Robertson and Seymour. This is like probably I will say the deepest in the graph theory or combinatories. This is one of the 500 pages. And it is interesting, like 40-page paper is just the proof of a lemma that will be used later by future papers. So lemmas can be complicated, but generally they are just simpler than main theorem. So here, this is the theorem that we have, and this is the lemma that we want to prove. So what is the lemma? What is the lemma? Lemma is somehow simpler ways, but this is the breaking the theorem to a smaller part such as we can prove it. What is the lemma? Is that adding one more line to n-1 lines in the general position in the plane increases the number of regions by n. So if you have n minus 1 lines, you will add one more line to that, then the number of regions will be increased by n. Good. So note that this is different from this one. We want to say that if there are we have n lines in a general position, the number of regions is this one. This is a simpler statement. Say that if you have n minus 1 lines in general position, you will add one more line in again, just everything is in general position, the number of regions would be n. Is the statement of lemma clear?
Yeah, that's clear.
Good. And this is just somehow smaller than this one. Theorem, I will write THM. Lemma, we will write it LM. Good. So now let's see if so this is the way that this is, oh, this is a complicated thing. How can I prove it? So maybe I can just try and say if we have n minus 1 and then add 1, how many things will add it? So let's try this one. And so that we should prove it. But say we have assume that this lemma is proved. That's the way that actually we are doing a lot when we are proving something. So, okay, this is some guess that I have it. Let's say this is correct. If this is correct, can I prove the main theorem with that? If it is the case, I have not proved the lemma yet. Then if that actually implies the theorem, it means that, oh, I have found something which is simpler and implies the theorem. Let me go and then prove that lemma. For the proof of one lemma, you may need to have some other lemmas as well. Sometimes we have this other thing, it is called propositions. Proposition. What is a proposition? It's just some maybe very trivial lemmas. We will call it propositions. But general theorems and lemmas are the main thing that you have it when you prove something mathematically. Okay, so let me just clear all the drawings. We are back. Good. So let's do this one. So let's prove this lemma. That adding one more line to n minus 1 lines in the general position in the plane increases the number of regions by n. Good? Clear? So, say, so if we want to say that if this guess or this lemma is correct, we are doing that. So, okay, for n equal to 1, we are done essentially. We know that the number of p's, the number of regions would be p of 1 is equal to 2. That's the example that we have just drawn. Now, let's set, what would be p of n plus 1? The number of regions of p. P of n plus 1 means that the number of regions of p n plus 1. So, then we have, we know that according to that lemma, the number of things would be n for p of n. And if I have it n lines and I add it one more lines, that will be increased by n minus 1. This is because of the guess, I will call it lemma. That's exactly the one that you need to write it here. So this is, again, you will define this. Why 1 is correct? Because of the lemma. Now, then you will just, if we have that one, then we are done. Because P of n, then we can use the induction hypothesis that we had it above. If we have, for this one, we are just using the induction hypothesis. Okay. And this comes from this fact that we had for the induction hypothesis. So if we can prove that if we are adding one more line to n minus 1 lines in the general position, then the number of regions will go up by n. Good. Now let's go for the proof of, so this is the lemma that we were talking about. So this is, we'll call it lemma. Oh, this one is working. Something went wrong with it. These things. Okay, so I can just do this one, but that is not the best one, but still better than nothing. When the thickness is small, it's not working. Probably if I reset, it works, but I don't want to reset because then the Zoom, you need to reconnect and then the recording will be disrupted. Good. Okay, so let's continue for now with this one. So is the plan clear? Now, we want to say essentially this one, that no, so we had that lemma that if we have n minus 1 lines, if we had one more lines, then it would be the number of lines that will be increased, the number of regions would be n. So if you have n minus 1 lines, you will add one more line, the number of regions will be added by, that would be n. Okay. Good. So we can prove that lemma itself by induction. So in some sense, we have two levels of induction. To prove essentially, we said that we have one lemma. If that lemma is correct, we guess that lemma, I said this lemma is correct, then I can prove the whole theorem by induction. But now to prove the the lemma itself, we may use induction as well. Good. So let's consider this case. So for consider this. So if we have, say, so this is the whole plane. If we have one line there, if we are adding one more line to that, how many regions will be added?
Two.
So that is correct. So for if we have one line, then we add one more line, then two will be added. Good. So that seems for n equal to the induction, basis of induction is correct. Now, let's see that, I mean, what will happen if we have essentially this one. Let's prove it for general. Say, we know that if there are n minus 1 lines and then one line is added, then the number of regions goes by n more. Now, we want to say that if we have n lines and then we add one more lines, the number of regions goes up by n plus what?
N plus 1.
N plus 1. Good. Now, let's see what will happen. So this is actually an interesting way of proving this one. So let's consider the first, so consider the whole region. And then first consider the, these are the first n lines in the page. Let me have another one. This one, say, so this is the nth line. And let me add another one. This is the line n plus 1. Good. Let's see what will happen. So, and these are the first n minus 1 lines. So the first n minus 1 lines are these blue guys. So these are the first n minus 1 guys. So the first n minus 1 lines in blue, then we have the n line and we have n plus 1. And we know that from n minus 1 to n it works. But we want to go from n to n plus 1. Good. Now, we will say, no, we are using actually induction in a very nice way here. We say that what will happen. So, so to prove that, so what do we want to prove? We want to prove for n plus 1. Say that, okay, remove the nth line for now. Good. When you remove the nth line, what will happen? We know that when we just adding this n plus 1 line, the number of lines goes up by how many?
N plus 1.
No. If the n line is not there, then the number of regions by induction hypothesis goes up by how many?
By n.
By n. Good. Now, so this is the one essentially that goes up by n. The only thing is that, okay, so, but here we want to get n plus 1. Here we didn't consider the line n. So this is the interesting thing that we considered actually in this figure. We will say that actually when you consider, so this was the case essentially for the regions that we had it for so if this is the region, so this is the one that we just write here. This is the region. And maybe I should write it as a different color. Let me write. Good. So consider this is the region. This was nth line. I think that the one that we have it. So let me have it. This was the nth line. It's here. This was the nth line, the same color that I was there. And the other guy was this. So these guys, we will say that there is one region, that the line n and n+1, they are intersecting. In all other regions, when there is this line, so in all other regions, it would be something like this. In all other regions, it would be something like this. That, okay, so in all other regions, it would be something like this that we have it here. So the n lines add one region, and the n+1 adds one more region. So in those guys, actually, this n+1 guy that has been added, actually just added one more region. So this, in those cases, we are fine. So when we are returning the nth line back, on those regions, nth line has his own region added, n+1 has its own added. The only region that might be problematic is the case that this n line and n+1 lines, they essentially intersect each other. Good. So here, that's essentially the interesting thing. So here, this is like the things that if we had this, so if we had the general region, so we had the general, so let me just draw it like this here. So yes, yeah. So let me actually do this. Yeah, so just, say that this green line is not there in this region. Good. If the green line was like this, then, and not this one that we have it here, how many regions did we had it here, added by line n and n+1?
Turn one into three regions.
Exactly. With one, it turned to three regions. Good. Yeah. But now that they are intersecting, now let's consider this one, that now these guys are intersecting each other. Then how many regions do we have?
4.
4 essentially, correct? So this region that these guys, they are intersecting, instead of adding each of them one more region will be added. Correct? So then we will get this n+1 things that we want. That's it. But this is actually, the way is a nicer way, that it's like a more advanced proof that we are using some lemmas there, and there inside the lemma, we are using another induction on top of the induction. And the type of induction is nice, actually, that we say that, okay, we will consider n+1 to prove it. We will remove the nth line. Then n+1 would be n, so there would be n regions added, but there may be something we are missing. What do we miss? The part that we are missing is that everything that is correct if these two lines, they don't intersect in that region. And we know, by the way, exactly this n and n+1, they are intersecting in how many regions?
They're intersecting in exactly one region.
Exactly one region, actually, because they are not in general lines because they are in general position. It means that they are not parallel with each other. It means that they should intersect in region, and there would be exactly one region. So exactly for one region, instead of the regular things that we had 3, we had 4 regions essentially added. So one more than the usual, and that's exactly this one. So there is exactly one region happens. So we get, instead of n, we get n+1, and that's it. So we got the theorem. Good. So here we are designing algorithms by induction. This is the one that I have measured. So what is the problem? So consider again, this is very similar. Setting is very similar to the previous case. We have n lines in the region. They might be not actually in a general position. So it means that some lines can be so we have some of these lines. They are not in general position. What's the meaning of that? It means that these two guys, they may intersect. 3 of them may go to one line, and there might be 2 lines here that might be parallel to each other. Good. And they are dividing the region into dividing the whole region into some sub-region. Good. This is the question. We want to say that this is the theorem that we want to prove. It is always possible to color these regions for find by any number of n lines in the plane. So any n lines, so any number of lines, it can be at any number of lines, by at most 2 colors. And what is the meaning of coloring? So the coloring is important. This is the thing that if 2 such that neighboring regions, what's the meaning of neighboring regions? If there are, so these 2, if you have 2 regions like this guy and these guys are considered neighbors. Any 2 guys that share an edge between them, a line between them, that will be called neighbors. And we want to have all neighbors have different, no 2 neighbors have the same color. However, so these 2 guys should be different, but these 2, that is fine if that we have something like this and both of them are blue. That is fine because these 2 are not neighbors. Only we cannot have this one. This is not acceptable that this guy and this guy are both blue. But if they share only 1 point, it is fine to have 1 color. Is the problem statement clear?
Yeah, that's clear.
Just please, if you have any question you don't understand, please ask question. Always I say that if you don't understand any part of the things, it is completely fine. I will go to some talks, I may not understand some part of it. That is totally fine and natural. But if you don't know something and you don't ask, that's the problem. Because you have the opportunity to ask, and that your question might be the questions of others. It is always good to ask questions if you can. Good. So the question that these regions that we are forming, we want to do that such that, we want to have, say, you can consider a map of lines, we have it, and you will see some more essential in the exercise. This set of lines that we have as a map, the question is that can we color them in a nice way? You will go there actually. If you, for example, now if there are some of these documents, for example, if there are, they may do it in 2 different, like even if you have a set of lines in text, I will say, such that they can distinguish it. The first one is black, the other one is gray, the black, gray, such that you will distinguish them. That's the same question that we have. Good. So any algorithm to do that? Do you have any ideas how can we design this algorithm? If you have any ideas, you can just mention. Good. So let's play a little bit with that. So we have, say, this is the whole region that we have. So and this is one thing that we have. So we have this is one line. If we color this one red, and then we will color this guy green. Good. Now we are adding one more line to this. Now, of course, we are violating because these 2 guys now, this guy and this guy and this guy and this guy, they are neighboring region and they have the same color. So we want to design algorithm by induction. What's the meaning of designing algorithm by induction? Say that, okay, with n lines we could solve the problem. What about if we have n plus 1 lines? Of course, say we have a way to color these n lines. How can we essentially design the things for n plus 1 lines? So say you have actually colored. So this is the way actually, if you don't think this way, the problem might be very complicated actually. You will try to color these guys and it can be actually quite complicated. But if you see the right way, and this is exactly this book, it just said very cute problem. cute way of looking differently on the problem such that you can solve it. This is almost always in all of these kind of interview questions, that if you go for one of these companies, you want to do that, you will see some way that you should do it, but this the first way that you should do it. You should not do it that way, because that's the trivial way and that's the wrong way, and it's a more complicated way. You need to find the other way. That would be the correct way. And the other way means that the tricky part, and that might be much simpler also, the implementation of the algorithm. Good. So this is the whole idea, essentially. Then you have colored with n colors, n lines. So these are the lines that you have done. It's like this is the other line that you have. Now let's see. I mean, I add essentially this. So this is the n+1 line that you are adding. What can you do? Actually, that's the way that is by induction. So we knew that for n, we have done the correct way. Now, what do we do for n+1? That's the thing that so for this part, so we know that this n+1, it divides the region into how many regions?
n+1 regions.
Yeah, but I mean, actually, it just by itself, if you consider it, it divides the whole page into 2 regions, correct? 2 sides of it.
Yeah.
What do we do? For one part, we will keep exactly the same color. For the other part, we will just swap the colors. What do we do? Essentially, we are doing, so for this one, we keep the color. So this red and green, we will keep it. For the other part, what do? We just replace the color. So I will just replace this one with that. And then I will replace this guy with green. Good. Now we are done. Why?
Because the coloring is now valid.
Okay, we need to consider 2 cases. So we need to say that no 2 neighboring edges, 2 neighboring regions have the same color. If these 2 neighboring guys are here and here, then by induction hypothesis, they had a different color, correct? And we didn't change the colors here. Is it clear? So is it clear? Please unmute and answer.
Yeah. So for like the
for this part that we didn't change anything, so everything was fine. Now the other region, so there might be these 2 guys are neighboring. I want to say still we are fine. We changed the color. However, we swapped the colors between green and red. So when they were different before by induction hypothesis, I swapped them, but I swapped both of them. Still, they should be fine. Correct? Does it make sense?
Yeah.
Yeah.
Good. Now, the only remaining things is that there is one neighbor from here and one neighbor here. So when we have one neighbor here and one neighbor here, this was one region before. When this guy came, it makes it 2 regions. But this one region was, say, in the previous case, the whole region was red. When we draw this one, we switch the other side. So the other side is now green and this guy is red. Or vice versa. This was green. We changed the other side to red. So both of them have the different color. So for any 2 neighbors, if they are in the one side of it, it is correct by induction hypothesis. And if they are one in this side, the other one in the other side, because of the way that the algorithm worked, actually we obtain. Good. So is it clear? Any questions?
So when you add in another line, you just have to change the colors at that intersection?
Not intersection. I mean, then when you add a new color, so for example, if you add another line here, then it again divides this one into this side and this side, correct? For one side, this is the same. This is the swap. Correct? So these guys, the all regions is this one, you will keep the region, the same color. For the other guys, you just swap the colors. And that's it. But that's actually a very nice way of seeing that. Any other way, if you want to solve this problem, it will be very complicated. Great. So yeah, I think we are done with this part. I mean, we will go, actually to annotation, and then we will come back again to see a few more of these nice problems. So that, by the way, just one question. What would be the input to this problem if we want to solve this one, say, for example, in the lit code or like HackerRank or other? What would be the, how can we decide, essentially mention the input to these problems? Output of this problem. So the input would be the number n. So this would be the way. So you have the number n, the number of lines. Then in each line after that, so each line of input, this is a text file. You have essentially two things. You have the slope and say 1 point that it goes there. So xy. Good. These guys, this a slope and xy, they say what is the line that you have it. Good. So in each line, in some sense, you have three numbers: the slope of the line and the point that it goes there. So each line will be determined by a slope and 1 point that goes through that. Correct?
Yeah.
Now, what will be the output? Also, we can say that actually we have this assumption. They say that we have a boundary of this. So we can start from 0, 0. And I don't know, they say the boundary of this is, I don't know, 10,000, 10,000. This is, should I say 1,000, 1,000. Good. Now, what else? What would be the output of this program? That would be one way, but it might be, yes, you can't say the whole thing is like consider it very fine grid and mention it. The other way would be something like this. You will say M, so I will say the output here. So you will say M, the number of regions that you have. For each region, you will say the points. So how many, so for each region, for example, for this region, you will write, so we have M regions. You will say number 5, how many points in this region? Good. Then you will see the xy of each of these points. So you have 10 numbers here to say the xy of these points around, say, in a cyclic order. And then at the end, you will say red or green. So in some sense, the output would be this. You need to say the regions that they have been formed, what are the points on the boundary of each region and the color of that. Is it clear? Actually a good example. So you see the input is easy. The algorithm is not hard, to say, but to get these things, you may need to do some work. I will actually, this is something that, I don't, this is not some assignment that you need to, turn in, but this is an assignment that you should do it, for yourself. Write a program, say in C++ or Python that do this job. Get this input and produce this output. Either of them would be fine, either C++ or Python. Get the input, again, n, a slope of each line, and xy for each line, and then write m, the number of regions. For each region, say how many points on the boundary, xy of those people on the boundary, and then say whether it would be red or green. So then you can test it actually and see how does it. But that would be a good programming exercise that I think you should do it. Again, you don't need to turn in, but that would be something that strongly is recommended. Like, not recommended, that is actually is assignment. You should do that. Write it in C++ or Java. You can do Java as well if you want. C++ or Python would be probably better. Good. So we are done with today's class. Any question?
So sorry for going back, but for like the other problem for the n region,
yes,
the region problem, how do we know that if the two lines weren't intersecting in that region, that each line would add n region.
Sorry. So in that case, actually, I think that was the idea. We remove the nth lines, and we say that the n+1 guy and n, they are somehow, I mean, on those regions, they are parallel. So they don't intersect. So the region that each of them adds would be separate from the region the other guy adds. Good?
Yeah, but okay. Yeah, so it's like in that case it would be parallel, so we know that the
exactly. So those guys would be parallel, only one region that they intersect. In this guy, they are adding, instead of each of them adds one, in total they are adding, instead of 2, they adding 3. And that's one other thing that we will give the credit for. Great. So